Okay, so excuse me. Last week we were looking at recurrent networks and various examples where we were processing sort of small-scale synthetic languages. So today we're going to talk about how to scale these things up to real natural language processing. Excuse me. So we're going to look at statistical language processing, n-gram models, co-occurrence matrices, word representations, particularly focusing on word2vec, and then some things we can do to examine those word representations, looking at word relationships, and then looking at some large-scale systems doing neural machine translation and other tasks. And finally, a little bit about some work that combines images and languages. So let's go back to the kind of philosophical underpinnings of this. So what is the meaning of meaning? If I give you a word and ask you what is the meaning of that word, well, you can write a definition in terms of other words. So you can look up a dictionary. Samuel Johnson compiled the first sort of large-scale dictionary in English, but the other dictionaries go back to ancient times, but that requires a lot of human efforts, of course. And then if you look up Roget's thesaurus or some of these online thesauruses, you'll see lists of synonyms and antonyms. So trying to group words together into groups that have I think that in Roget's thesaurus there's about 1,000 different categories and quite a few words in each category. Or you can look at taxonomies of words. So there are these, again, online repositories like WordNet and so on, where you look at the relationship between words. So it can be a hierarchy where you say a penguin is a type of bird, and a bird is a type of mammal, and a mammal is a vertebrate, and so on. Now, all of these are useful, but they have certain limitations. So first of all, let's look at synonyms. In Roget's thesaurus, these are all synonyms for the word elegant. Stylish, graceful, tasteful, discerning, lovely. So some languages like English have really a huge vocabulary, which is very sort of nice. I mean, Chinese and classical Greek also have quite a large vocabulary. In most cases, it's because they've borrowed from a lot of other languages. So you can express very fine nuances between different words. But as I said, first of all, these things require human effort to put them together. And they may be incomplete or require choices. Some of these things you may sort of have some disagreement about whether it's really a synonym for elegant or not. I don't know, modish. What is modish? And then by grouping the words together like this, the nuances are lost. The thesaurus is effectively treating all these words as being the same, but in fact there's slight differences, and some linguists have argued that that you can find semantic differences between any pair of words. That there's no such thing as absolute synonyms. I think George Lakoff was one of these people. He said, if you give me any two words, I can tell you some difference in meaning between those two words. So like and enjoy, for example. I like this chair. I enjoy this chair. Are they different? Well, if you say you enjoy the chair, that implies that you actually make use of it. That you sometimes sit on it. But if you just say you like the chair, it might be that you never actually use it. You just think it would be a good idea. So there's always, you can always draw some fine distinctions like this. Now, and then we talk about synonyms and antonyms. So an antonym is meant to be things that have opposite meaning, but when you really think about it, that's a pretty crude idea, and in fact, well, the opposite of big is small. Well, that sort of makes sense, but those two words are similar in a way because they both describe the size of something. And similarly, words like king and queen, in certain contexts, they can be considered as antonyms. Well, they are similar. Are they, as king and queen, are they synonyms or not? Well, they are. They both describe, rulers. They're similar in most respects, but opposite in some aspects. So any pairs of words, you tend to get this kind of multifaceted relationship, that they have some similarities and some differences. So this all gives rise to the question, well, instead of relying on these sort of, incomplete as well. There may be other words that are similar to elegant that someone just failed to pick up on, or whole categories that someone failed to include in the list. So could we instead have an automatic process that extracts statistical properties of words without human involvement? Now, I've decided to use this simple children's rhyme just as an example to illustrate some of these ideas. Yeah, some of you may be familiar with this. There was a crooked man who walked a crooked mile and found a crooked sixpence upon a crooked stile. He bought a crooked cat who caught a crooked mouse, and they all lived together in a little crooked house. Nice little children's rhyme. So what can we say when we look at it? How can we analyze a text like this? If we let's think of this as a document. So let's first of all think that we're doing document classification, and this is one of our documents, and we have a collection of other documents, and we want to somehow categorize them. Well, we could count how many times each word occurs in that document. So what you notice is, there are some words that occur frequently in all documents. So words like a and occur in a lot of documents. They're just generally very common words. The is also a common word, although it doesn't actually occur in this particular document. But then there's some words that may occur frequently in a particular document, but are not generally common. So in this case, the word crooked appears 7 times. And this is actually, you may think that this is unusual, but in fact this is typical, because if you think of a document, if you think about what other kinds of documents we tend to deal with, so if a document was the instruction manual for a refrigerator, then the word refrigerator might occur a lot. If it's a legal document relating to custody of children, then custody and children would occur. So it's actually in any kind of in any document you tend to see these words that occur many times in that document. And so, once we have this information, this gives us the idea this could be useful to try to classify different documents. So let's imagine this is one of several documents. This is document number X, and we also have document 1 and document 2, and so on. And there's really a lot of different words, perhaps 60,000 words that could occur, and we just mark which words occur in a particular document and how many times. So if we have this information, how would we use this to do document classification? Okay, so notice, right, so let's just remind ourselves what's going on. This becomes a kind of matrix, And the number of rows in the matrix is the number of words in the dictionary, which, is, as I said, is typically about 60,000. And the number of columns is the number of documents in our collection, which might be also 10,000 or 20,000, depending on the application. So, yeah, but the numbers are different. Now, what you notice from this, okay, so there are certain words that, so this document is obviously a children's rhyme, and there are certain words that tend to occur quite a lot in children's rhymes. So words like cat and house and mouse occur in a lot of different children's rhymes. And then there may be other words that are characteristic of other types of documents, legal documents, political news, sporting results, and so on. I think you could, if I gave you a category, you could probably come up with a list of words that are likely to occur in that category. Now, sometimes, this is the typical thing, but as I mentioned, when we want to sort of analyze this as a matrix, sometimes we just get rid of the numbers and just put a 1 to see if that word occurs at all in the document, then we just put a 1. Because those funny words like crooked might sort of skew the results, and so sometimes it's just like a 0-1 matrix saying whether something occurs or not. So it sort of depends a bit on the application. Now, another thing we can do, if we're not looking at document classification, but we're looking at other sort of tasks like translation or predicting the next word or generation, then we often look at we could look at what words tend to follow other words. So we can make this matrix that counts the consecutive pairs of words. So here again we have all the words down the rows and all the words across the columns. And we note that A, in this particular document at least, the word A is followed by crooked 6 times, and it's followed by little once. And crooked is followed by cat once, and house once, and man once, and mile, mouse, sixpence, and star. And so we get this sort of matrix. Now notice this is kind of different from the other matrix. So it's words against words, and in this particular case, it's taking account the order of the words. So this matrix is not symmetric. Now, what can we do with this? What can we do with this kind of matrix? Now, again, like from just one document, you don't really get much. But if we aggregate a lot of documents together, you might get a pretty good estimate of the statistics of one word following another, and you can actually turn this into a probability distribution. So if you look across a row, if you look at the word crooked, again, this is just from this very small document, but we would deduce perhaps that crooked has an equal chance of being followed by each of those 7 words. So we normalize, if we want to treat it as a probability, we normalize it by dividing by the sum of all the entries in the row. So we get this matrix where the sum of every row is 1. And we can use this as so this is called a 1 gram predictive model, and we could potentially use this to generate text randomly. So we could start with one word, and then we could choose from the probability distribution of what's likely to follow that word, and just choose the second word, and then do the same thing for the third word, and so on. Then we get what's called a 1 gram model, and we can generalize if we take account of if there's 2 words, what's the probability distribution for the words following those 2 words or 3 words. So we got a 2-gram model, a 3-gram model, and eventually an n-gram model. Right, so yeah, so we need to normalize each row to add to 1. We need to aggregate many documents from a large corpus to get meaningful statistics. But even looking at this, you can see that this already captures some common combinations of words, right? So there was man who and found, he bought, who caught, and they all lived together. These are phrases that actually are pretty common, not just in this particular document, but generally. Now, as I say, we can generalize this to a bigram or trigram model, but if you think about the memory requirements, so again, I keep coming back to the 60,000. So if you, in order to store a 1-gram model, you need a matrix that's 60,000 by 60,000. That's pretty cheap, but then theoretically, if you wanted a 2-gram model, you'd have to multiply again by 60,000, and for an n-gram model, it would be 60,000 to the power n. So people have certain tricks that allow them to get an approximation without having to store all the possible combinations. And this is, I actually just did this myself as a bit of a test. I generated the I took Shakespeare's Hamlet as the input and just generated a 1-gram model from the entire text of Hamlet. And then you can play this game of generating the words one at a time based on the probability of what follows the previous word. And if you read this in a proper Shakespearean accent, it may sound slightly plausible if you don't listen too hard. You know, rashly, good knight is very liberal. It is easily said that there is gyve to a sore distraction in wrath, and with my king may choose, but none of shapes and editing by this, etc. Transports his wit, Hamlet, my arms against the mind impatient, by the conditions that would fain know which the wicked deed to get from a deed to your tutor. So it sounds, if you just listen to a few words at a time, it sort of sounds plausible. But then when you look on a larger scale, you realize that it's just total nonsense. And there were famous websites which, there was a website called the Postmodern essay generator that originally just had a very simple model like this. Later, I think that website still exists, but the generative model is a little bit more sophisticated than what it used to be. Okay, but this is not, you can easily, the global structure obviously is not very good. Okay, so what can we do to do better? Well, what we can do is generate a co-occurrence matrix. So this is similar to the 1-gram model, but we actually get a symmetric matrix. We don't worry too much about the order. Excuse me. So if A follows B, we forget about whether A follows B, we just want to know whether A and B occur next to each other or near each other. Or more generally, whether 2 words are likely to occur with, if you pick one word, what's the likelihood that another word will occur within a certain window? Maybe I look at 5 words on either side, so I look at 10 neighbouring words altogether. What's the likelihood that the other word will occur within that, within 5 words of this word? Okay, so if we do that in this case, this is what happens. Now, this is just looking at one word on either side. So you get a very sparse matrix here because we're just looking at absolutely neighbouring words. Now again, we'll just remind ourselves, so the rows are labelled by the words in the dictionary, and so are the columns. And it's a symmetric matrix. Now here we've expanded the window to a 10-word window. So like I said, 5 words on either side of the center word. And we see a lot more structure now. And this is just from one document, and then we can go through and do the same thing for many, many documents, and we get this big matrix. Now, so what we really, our overall aim here, so let's think about what we're actually trying to achieve here. So what we want to do is we want to use one of the models that we discussed last week to process language. And so the inputs to this, so a recurrent network or an LSTM, and the inputs to this model are going to be words. But so we want to have effectively what we want to have is a vector representation of each word. Maybe there's a set of 200 inputs for the model. And we want to have a vector of for each word, we want to have a vector of 200 numbers to put into our model. And we want to generate these vectors in such a way that similar words have close vectors. Right? So, elegant and foppish, or whatever that word was, all those synonyms for elegant hopefully would have nearby vectors in this vector space, and it would be generated automatically without a human trying to impose it. So this co-occurrence matrix, in a way, does that for us. So, we could treat each row of this matrix as a vector. Again, let's imagine that we do this over many, many, many documents. And we've got 60,000 words, so if we look at a word like, crooked, we could look across we'd have a vector spanning this row, and we could treat that as being the vector representation of the word crooked. And this row could be the vector representation of the word mile, and so on. So for every word, we could treat that corresponding row as the vector representation for that word, and we hope that 2 similar words would have similar vector values, because if 2 words really are similar in meaning, then they should theoretically occur in similar contexts, so the words surrounding them should be similar. So this solves the problem of giving us a vector representation. The problem is that the dimensionality is way too high, right? It's 60,000. So we want to reduce that to a manageable number, perhaps 150, 100, 200, perhaps 400 or 500, something in that range, somewhere between 50 and 500, but not 60,000. Okay, so just also pointing out the properties of this matrix. Again, this is what we can actually deduce just from looking at this. When we've moved from just looking at neighbouring words to looking at a 5-word window, new relationships appear that weren't visible before. So we can see that words like cat, court, and mouse often occur close to each other. Not necessarily next to each other, but within that 5 words window on either side. Walked and mile, same thing, little and house, right? So we can start to see some of these relationships. Now, again, there's this issue which we'll come back to later, like common words tend to dominate this matrix, right? So crooked is a funny word that's sort of common here, but not generally. But if you aggregate it over multiple documents, there are certain words like the and so on that are very common generally. So sometimes we modify this matrix by sampling frequent words less often and stuff. So we'll talk more about that later. Okay, now this idea that I was explaining about the meaning of a word being determined by the context, the first people really to talk about this were these structural linguists back in the 1950s, Harris and Firth. So yeah, words that are used and occur in the same context tend to purport similar meanings. You shall know a word by the company it keeps. Yeah. So this is the aim that we have, is to find a vector representation of each word, such that words with nearby representations are likely to occur in similar contexts. And this is a slightly more kind of detailed history. So as I mentioned, these structural linguists in the 50s. We talked about these recurrent networks in the 1980s. But then the idea of actually assigning a vector to each word, that first was introduced in 1990 by D. Wester under the name of latent semantic analysis. And then various models building on this: hyperspace analog to language, neural probabilistic language models, Bengio. So this 2000 paper is getting quite close to the modern day approach. And then NLP from scratch, and then these two models that are the most commonly used ones. So this word2vec we're going to describe in quite a bit of detail. GloVe is an alternative to word2vec that I'm not going to talk about too much, but they both do a similar job. So this is an example of how the words from that particular poem might be if we might be put into a two-dimensional vector space. So let me tell you how this can be done. All right, now, so we have this co-occurrence matrix. So if it's a word-word co-occurrence matrix, it's based on this 10-word window. But if we were doing document classification, the same principles apply. In that case, the rows of the matrix would be words, and the documents would be the columns would be documents, right? So this co-occurrence matrix, we describe it as being L by M. So L is the number of words in the lexicon, and M could be equal to L if it's word co-occurrence, or M could be the number of documents if you're analyzing documents. Okay, but they're not necessarily equal. Now, this is where we need to know a little bit of linear algebra. So it turns out that if you write down any matrix X, so this is a matrix, if any matrix X can be decomposed in what's called the singular value decomposition, it can be written as a product of three matrices, U, S, and V, or U times S times V transpose, with the property that S is diagonal, with the property that U and V are unitary matrices, and S is diagonal, with non-negative entries. So in general, the size of these matrices are as follows. So X is L by M, U will be L by L, V is M by M, and S is L by M. And yeah, so S only has entries on the diagonal, and U and V are unitary. So unitary means that if I look at any column if I look at any row in this matrix U, then the length of that vector is 1. Yeah, so this is so in other words, it determines like a orthonormal basis of the source space and the target space. Okay, so some of you, if you're a bit rusty on the linear algebra, you may have to brush up on this a little bit. I'll try to say a little bit more about this in its relation to eigenvalues, but you might have to do a bit of background reading about this. So where are we? Oh yeah, so unitary. So this is a slight. Remember this is L2 normalization, not L1 normalization. So previously when we were talking about probabilities, we had the sum of the rows, the sum of the items were every item was positive, and the sum of the items in a row was always equal to 1. Here the individual entries in the matrix can be positive or negative, and it's the sum of the squares of those numbers that are equal to 1. So if you add up the sum of the squares of all the numbers in this row, you get 1, and the same thing for every other row. And these rows are all orthogonal to each other. So another way of saying, if you multiplied U by U transpose, you'd get an identity matrix. And the same thing with V. And then S only has elements on the diagonal, and things off the diagonal are 0. Okay, so in general, the singular value decomposition the matrices would have that size there. But if we want to have what we want is an approximation to X of lower rank. So we choose some number n less than m, and we truncate these matrices. So when I've written U tilde here because U originally had size L times L. U was actually a square matrix, but I've chopped off most of the columns, and this is all I have left. And remember, these numbers are quite large. So in a typical application, L would be 60,000, and N would be 200. So I've taken a matrix that's 60,000 by 60,000, and I've chopped off almost all the columns. I've only got 200 columns left. And the same thing with V. I've chopped off rows of V transpose, so I've only got 200 rows left. And this matrix in the middle has also been chopped. So the original S was L times M, but I've just, so it was a much larger matrix as well, but I've just only taken this small piece in the corner, which is 200 by 200, right? So I've chopped these matrices down significantly, but if you look at the numbers, you'll see if I multiply these three matrices together, the product of those three matrices will have size L times M, and it is an approximation for X. So that's why this is not an equal sign, this is an approximately equal sign. And now what's happened here is, now notice these are the singular values here, these numbers, and these behave somewhat like eigenvalues. So I'm aware that some of you may be familiar with the eigenvalue decomposition of a matrix, but not the singular value decomposition. So I'll say in a minute some relationships between the two. but we order these numbers. These singular values are all positive, and we order them in order from largest to smallest. And it's the largest, when we chop the matrix down, it's the largest values that we keep. Okay, so this is somehow related also to principal component analysis. And there's a sort of, there's a fair bit of mathematics behind this. If you look at the Wikipedia page for singular value decomposition, there's actually a lot of information there. But there's basically a theorem which roughly says that if we want to find three matrices with these dimensions and these properties such that their product is approximately equal to X, then this is in some sense the best we can possibly do. This is the best possible approximation to X in terms of the Frobenius norm of the difference or something like this. So this is approximating X, but doing it with smaller matrices. So matrices with smaller rank. And so once we've obtained this, then we can treat these vectors here as vectors for our words. So word K, in the original matrix, so we originally had L numbers in this row, but we've chopped it down to K, or we've chopped it down to N. So we originally had 60,000 items in this row. We're only looking at the first 200 values, but that gives us a two-dimensional vector. So we've kind of, what's another way of thinking about this? We've rotated, so U is unitary. So U has rotated, when we apply U, we've actually rotated the original space in a way that preserves all of the angles and the distances. And then from that, we're extracting out the 200, from the 60,000, we're extracting 200 dimensions, but we're not just randomly picking 200 dimensions, we're picking the 200 dimensions which preserve as much information as possible. Okay, so are there any questions about this? Okay, so all these things are based on this idea of the singular value decomposition. Now, the problem with this, for a very small matrix like our this one here, there was a crooked man, we can just, if we fire up MATLAB or Mathematica or Octave, we can just type in this matrix and ask it to do the singular value decomposition, and that's actually exactly how I've obtained these numbers. I've done a singular value decomposition and I've extracted out the first two components, but in a serious application where these numbers are of the order of 60,000, it's actually too computationally expensive to do this decomposition. The best algorithm for finding a singular value composition is cubic. So if L and M are different and M is the smaller of the two, then it's L times M squared, right? So if L and M were both equal to 60,000, then the time to compute this would be 60,000 cubed, which is too large. We can't possibly compute it. Okay, so what can we do? Well, what we want is a process that will approximate this or do something sort of similar to this, or approximate it in some sense, but in a way that's computationally more, requires less computation time, but still produces a reasonable answer. And as I said, there are two popular methods for doing this. So the one we're going to look at in detail is word2vec. The other one is glove. Now, so word2, they're both, as I said, essentially do the same kind of job, but word2vec is a predictive model, so it's trained to maximize the probability, well, it's trained to predict the probability of a word occurring within the neighborhood of some surrounding words, and we have to maximize the accuracy of that probability. Glove is a count-based method, and it's basically more directly tries to reconstruct this matrix X. So this is actually trained based on how well it reconstructs the co-occurrence matrix X. Okay, so glove. Now there's a lot of these two things appeared around the same time in 2013, 2014. There was a lot of very amusing discussion about this. There were there was one blog that was claiming that glove is superior to word2vec in various ways. There was another guy who had a blog. He was saying that actually the two are give pretty similar results, and there was this kind of flame war going back and forth. So, you know, bring your popcorn with you. The consensus, speaking today, I think people tend to think that glove gives a little bit of a better result than word2vec. But word2vec is simpler, so that's the reason we're actually going to look at word2vec. And if you're interested in glove, you can go and look at it on your own, what the details of that are. Okay, so let me just, try to, because some people, I know people will ask about this. So how does this relate to the eigenvalue decomposition? So here's some examples of some very simple matrices. So you consider the matrix 0, 1, 1, 0 or 0, minus 1, 1, 0. So this first matrix is a reflection matrix. It swaps two coordinates. This is a rotation matrix. It rotates the space by 90 degrees. And if you compute the eigenvalues of these two matrices, what you find is that this matrix has a negative eigenvalue, and this actually has complex eigenvalues, right? So in general, this can happen, but the singular value decomposition never has negative or complex eigenvalues. It always has positive. The singular values are always real, and they're always positive. They're always non-negative. They're never negative. So this would be the singular value decomposition of these two matrices, and so so what is the relationship actually between the eigenvalue decomposition and the singular value decomposition? Well, the two would be the same if X is symmetric and positive semi-definite, then then these two decompositions would be the same. Okay, so a matrix. How can you tell if a matrix is? It's easy to tell whether a matrix is going to have real or complex eigenvalues. Symmetric means that if you flip the matrix on its diagonal, you get the same thing. So as I mentioned, this matrix here is symmetric. The value here is the value here. So if I reflected all these values in this diagonal line, the matrix would look the same. That's called symmetric. So if a matrix is symmetric, then the eigenvalues are going to be real. They're not going to be complex. There won't be any square root of -1. But they'll be real, but they might not be positive. So there's no simple way of telling whether the matrix is going to have positive or negative eigenvalues. You just have to compute them and see what happens. So this is the story that if it's symmetric and all the eigenvalues are positive, then it's the same as the eigenvalue decomposition. If it's symmetric but some of the eigenvalues are negative, then the two things are different. And if it's not symmetric, then it's definitely different because the eigenvalues are complex. Okay, so I'm sort of going into some detail about this because it is sort of confusing when you first see this. You think the matrix is symmetric, so you think you'd be looking at the eigenvalues, but the thing is that we want positive values, not negative ones. And the most simple example we can possibly think of is the following. Let's suppose you have a language. Let's suppose you have a language that has only two words, A and B, and the language consists simply of the alternating. It's always like A, B, A, B, A, B, A, B, A, B, A, B. That's the entire language. What would happen in that case? Well, the co-occurrence matrix would essentially be this. So A is the context for B and B is the context for A. And so the co-occurrence, if this is AB and AB, this is the co-occurrence matrix here. And as you can see, it's symmetric, but it has a negative eigenvalue. So really what we want to be looking at is this singular value decomposition. And this tells us, sorry, I skipped one point here. So even if X is a square matrix and the rows and columns are indexed by the same words, the singular value decomposition nevertheless treats the source and the target space as if they're totally different. It doesn't try to identify, it doesn't think of X as a map that goes from a space back to itself. It treats it as a map going from one space to another space. And these two spaces happen to be isomorphic, but we treat them as two totally different spaces. So U and V, U imposes a coordinate system on the source space. One of these U imposes U imposes a coordinate system on the source space. V imposes a coordinate system on the target space, and they're totally different coordinate systems, even if the source and target space were originally the same. And yeah, as I said, if you think about this AB, 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 we're not interested in the question of whether a word is in the context of itself. We're interested in other words, in its context in terms of other words. Okay. Any questions about this? Good. Okay. So now I'm going to move on to word2vec. How does word2vec work? So we finally get something that kind of looks a little bit like a neural network. But so looks a bit like a neural network in the sense that we have inputs, we have hidden units, and we have outputs. But this is unusual, or it's not like the other neural networks we've looked at before because there are no activation functions. This is a purely linear model. So we have weights. The hidden units are a purely linear function of the inputs, and the outputs are a purely linear function of the hidden units. There's no tanh or ReLU or anything like that. It's completely linear. Okay. Now, this V, okay, I've tried to make the notation match up as best as I can. I took these diagrams are taken out of the a paper describing the word to vectors, a reference at the end of the slides. So the one change, so n, this n is the same n from before. The one change is the V. So they use V to be the number of words in the dictionary. I used L because I already used V for this. I didn't want to have two V's. But so L has now become V. V is this figure of 60,000 that I keep talking about. So we've got like 60,000 words in the dictionary. So these things are numbered from 1 to 60,000. And then let's think, to make it concrete, let's imagine we have 200 hidden units. And so we take a pair of words, we look at this very large corpus and we're scanning the text and we find two words that occur very near to each other, within 5 words of each other. And so we pick one of them to be the input and one of them to be the output. So that's what this network is trying to predict, is what words are likely to occur near to that word, right? So if it happens to be word number k, if the input word happens to be word number k, we have a 1. Xk will be, that kth input will be equal to 1 and everything else will be equal to 0. But when you think about that, what does it mean? This is like a matrix that's V by n. So if this input is 1 and everything else is 0, for that particular word, it's only the weights from this unit that are important. All the other weights are not used, only these weights. And because this is 1, effectively what happens is that these weights get copied into those hidden units, right? So if xk is 1, then wki gets multiplied by 1, and so that becomes hi. Yeah, so the weights here are actually just the hidden unit activations for that word, or the vector representation for that word. Is that clear to everyone? So that's this half of the network, right? So that tells us the hidden unit activation. Now remember, this is where we think back to our geometric analysis. So that effectively, that's like a point. Remember when we had a particular input and we treated it as a point in the hidden unit space? Well, this is exactly the same thing, except it's a 200-dimensional space instead of 2 dimensions. And then the output is going to be like, we thought about the output as if it were a line. So here it's not a line, but it's a linear function on that hidden unit space. Yeah. So so let's look at that. So what happens at the output? Well, again, I'm just looking at a particular word, yj. Excuse me. So this is the target word, and okay. So the output, as far as the input is concerned, I can just ignore all the other weights. As far as the output, it's a little bit more complicated. I can't just ignore the other weights. I have to deal with it as a probability distribution. But if you think about the probability, or if you think about the output for a particular word j, it's just this hidden unit activation vector multiplied by this, the jth column of this matrix. Okay, so the kth row of this is the kth row of this matrix is the representation of k. And the jth column of this matrix is a representation for the word J, but it's an alternative representation. So this is where I was at pains to say that the U and V impose different coordinatizations. Okay, so again, just to go back to this, so effectively what's happening here is where the input to hidden weights and the hidden to output weights are meant to take the place of these two matrices U tilde and V tilde, right? This has become the input to hidden weights in the network. That's become the hidden to output weights in the network. But instead of doing this decomposition, we're going to just try to train the weights to do this, to reproduce these probabilities. Okay. Any questions about this? Yeah. I know this is quite a bit of linear algebra. Okay, so what we're looking here is we put in a word xk, and then we want to look at the probability of this yj. And so when you actually compute this, it's vk is the when the input word is k, the hidden unit activations are going to be the kth row of this matrix, which we call vk. So vk is going to be equal to h. And then this function here computes a linear function on that vk. Well, we take the kth row of this matrix and we take the jth column of this matrix and we multiply that row by that column and we get a single number, and that number determines the probability of this word. Okay? And then theoretically, we'd like to use softmax to calculate the probability, right? So this is the output for that unit, and we get outputs for all of these, and then we take e to the power of that number. In order to turn it into a probability, we take e to the power of that number, but then we have to normalize it to turn it into a probability. So the probability of word j occurring in the context of word k is e to the power of that linear combination, but then we have to divide by the sum over all possible words of e to the power of that combination, right? And this, unfortunately, that normalization is very important to the model. We can't just ignore it. We have to deal with it in some way. So if we had enough computation time, what we would do, right, so we treat the text as a sequence of numbers. So W1, I apologize, there's two different indices are being used for two different things here, but we say, when we say W1, W2, WT, we think of this as just a number. So if W1 is equal to 7,523, that means that the first word in the text is word number 7,522 in the dictionary, right? So we can turn once we've numbered if we go through and extract out all the words that occur, and we number them, give each one a unique number, then we can turn the corpus into just a sequence of numbers. And then what we want to maximize is the log of the probability. Okay, so again, these expressions look a bit scary when we first see them, but if you just break it down by components, it all sort of makes logical sense. So this is saying I'm looking at the entire corpus. I might have a string of if it's a billion-word corp, Google released this billion-word corpus extracted from different sources, so T could be a very large number, but I scan through the entire corpus, and for every word in the corpus, WT, I look at all the neighboring words. So C is the size of the window, so typically C is equal to 5, so I look at R ranges from all numbers from -5 to +5, but excluding 0, and then I take WT plus R. So I look at the 5 words that occur on this side and the 5 words that occur on that side of the middle word, and I want to know what's the probability of that particular word occurring in that window, right? And I want to maximize the log of that probability. So the aim of this is to, so remember what we're choosing is these weights here and these weights here in a way that will maximize this probability. Does that make sense? Yeah. Okay, where are we? So this is just okay, so this I think summarizes what we've been talking about. So it's a linear model. There's no activation function. Now, it can be applied in 2 different ways. One way is called continuous bag of words. The other is called skipgram. These are more or less 2 ways of doing the same thing. In one case, we're taking the middle word and using it to predict the surrounding words. In the other case, we're taking the surrounding words and using it to predict the middle word. But in theory, it should give the same answer. Okay, well, these are just the mathematics of this. We'll go through this in a minute, but there's one maybe I'll just make one main point, and then we'll probably take a bit of a break, and then we'll come back, because I realize there's been quite a lot of information here. Maybe we need to oxygenate our brains a bit before we dive back into this. So there's a key point about this, which is computational efficiency. So if you look into this, if I was really going to apply this, so this all looks quite straightforward, but the real problem here is this summation. Because if I really was going to apply this as it stands, okay, I'm processing through my text, I pick a word, I pick the 10 surrounding words, that's all very manageable, right? I've only got to train that word against 10 surrounding words. But for each combination, the problem is this: for each combination, maybe this is the word that actually occurs, but there's all these other words that didn't occur. So what I would have to do is not only compute the output for this, but I'd have to compute the output for everything else, and then I would have to use those results to apply the softmax. So and that would be very, very expensive because there's 60,000 other words. Yeah, so I go through my text, and for each word I would have to look not only at just at the 10 words that do occur, but 60,000 other words that didn't occur. And it's too expensive to compute that, so we need to have some tricks to make avoid that somehow and do it in a more computationally efficient way. Okay, and there's two tricks for it. One is called hierarchical softmax, and one is called negative sampling. All right, so we'll take a 10-minute break here, and when we come back, we'll look in detail at these equations, and then we'll look at those tricks and how they work. Oh, sorry, the lecture was suspended. Okay, so if you're watching the video, you didn't actually miss much. I just went through these. I went through these equations here, which you can look at yourself, and then I was just explaining the difference between the skip-gram model and the continuous bag of words. So this is the continuous bag of words. So the output is the center word, the input is the 10 surrounding words. And it's interesting to compare this with NetTalk. So if you remember with NetTalk, we had a window of 3 preceding letters and 3 following letters, but we had different weights depending on the location of the letter. Here, we actually share the weights. All of these 10 words share the weights because we're not interested in whether it was 1 word back or 2 words back or 3 words back. We're only interested that it occurred. And yeah, so this is the continuous bag of words model. Now the skip-gram model does it the other way around. We put the center word as the input, and then we try to predict these 10 nearby words as the output. Okay, so now we get back to this issue I mentioned about the computational complexity. So in theory, if we wanted to apply this, we would have to compute the input is not a problem. The input, we just put in the words we want for the input, and we don't care about the other words. We don't have to worry about it. But the output is the problem. To calculate this probability, we would have to look not only at the word that occurs, but all the other words that didn't occur. And we'd have to calculate all these outputs, and it's too expensive to do that. So there are two different methods for solving this. Now, one of them is called hierarchical softmax. And I just remind you that after we've trained the whole system, it's only this part of the system that we keep. We throw that part away, right? Because this is giving us a representation of the words. Theoretically, that is also giving us an alternative representation, but we don't worry about this part. When the training is finished, we just throw this away and we only keep this. Okay, so it's important to keep that in mind because I'm about to replace this by something else. And this is, I think it was Joshua Bengio who came up with this idea back around 2000 or 2002. And the idea is, okay, I want to say, I want to specify a particular output word. But what I'm going to do is, and I want a probability distribution over all output words, and I want it to be a legitimate probability distribution that's properly normalized. So what I'm going to do is I'm going to put all the words into a tree. And I'm just going to more or less do it in a random way, but it's going to be what's called a Huffman tree. And if you don't know what a Huffman tree is, that doesn't matter too much. What it basically means is that so each word has a frequency. I go through the entire corpus and I calculate the frequency of each word. And a Huffman tree simply says that at each branch of the tree, I try to put equal word. I try to design it so that at each branch of the tree, the total frequency of the words on the left-hand side is approximately equal to the total frequency of all the words on the right-hand side. So I try to make it so that if I added up the frequency of all of these words, it would be approximate. Well, if I think about the root node, if I were to add up the frequency of all of these words and add up all the frequency of these words, the frequency of these words would be approximately equal to the frequency of these words. So in other words, we're branching to the left or the right approximately equal. Not exactly equal, but approximately equal, as close as we can get it. And that happens at every branch of the tree. So in this case, this word would occur, the frequency of this word would be approximately equal to the sum of the frequencies of those two words. So there's a relatively simple algorithm for doing this. Basically, you just kind of list all the words in order of frequency, and then you start merging them together from the bottom up. You merge the two words that you merge the two words that occur least frequently into a little tree, and then you reinsert that into the list, and then you just keep repeating the process. So it's you can look it up, or most of you probably have seen it in your data structures course if you've done the data structures course. So it's a Huffman tree, but other than that, the interesting thing is that other than that, we don't really usually we don't take account of the meanings of the words. We just want the tree to have this Huffman property. Okay, now why is that useful? Well, it gives me an alternative way of estimating the probability of each word. So I have in my network, I have one output corresponding to every node in this tree, every internal node. So I have the same number of nodes as I had before, but when I apply the network, I don't evaluate every possible node. I only evaluate the nodes that occur on the path to the true output. So if this is the word that actually occurred in the context, then I know that I've got a branch this way and then this way and then this way, and at each node, the output at each node is just telling me the probability in that context of branching to the left or the right. And it's done with if the output of that node is u, then I calculate the sigmoid of u, and that gives me a number between 0 and 1. And so the network tells, if I evaluate this node, I know the probability of branching here. And if I calculate this output, I know the probability of branching here. And if I calculate this output, I know the probability of branching here, right? The probability of branching right is 1 minus the probability of branching left. And so if I just evaluate only these three nodes, I get three probabilities and I multiply them together, and that gives me the probability of this word, right? And so it's a genuine probability. You can see that all of these, I haven't bothered to evaluate everything else, but you can see that if I were to evaluate the probabilities for all the words, they would sum to 1. So this is a very clever idea, because it's a genuine probability distribution, but I don't have to evaluate all the other nodes. I only have to evaluate the nodes that actually occur on the branch towards this word, which on average is the logarithm of if the total number of words is n, usually the number of nodes I have to evaluate is only log of n base 2. Okay, so it's a very nice idea. If you look in the paper, it's a bit hard to come up with a notation that actually explains it. I've copied this from their paper. This is probably the best way you can do it, but this is just an attempt to write in equations what I've just explained. So the probability of a particular word is the product of the product over all the nodes that you go through to get to that word of the you calculate the sigmoid of that output, and then depending on whether it's the left, this notation here is just telling you whether it's the the left child or the right child. And then you multiply by that's the output of the node right there, and then this is the, this, oh gosh, I think there's a, sorry, these square brackets here just indicate a 1 or a 0 depending on whether it's the left child or the right child, and then we apply this sigmoid function. Okay, hierarchical softmax. So any questions about this? Yeah. So it is sort of interesting when you try to think geometrically what this is doing. This is sort of, we replace these outputs by another set of outputs that are the nodes in the tree, and each node is linearly chopping this space into two pieces. So this is you've got the hidden space is 200 dimensional. The root node chops the 200 dimensional space into two pieces, and then the next node will chop 1/2 of that space again into two, and then the next node will chop whatever remains. So it's like you start with the whole space and you chop, 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 and end up with some tiny little piece, which is where that the word actually ends up residing. Okay, so but that's happening on this end, and then what we really end up, the vectors that we save eventually are these ones. So the tree, it's sort of interesting because the tree imposes this kind of weird tree structure inside this 200-dimensional space. But I suppose to me the most interesting thing is that you would think so attempts have been made. Well, the interesting thing is that this tree was made just arbitrarily. You know, we tried to balance the tree, but we didn't make any attempt to put similar words close together in the tree. So there have been some attempts where you try to put similar words together in the tree, either using WordNet taxonomies or pre-training or some other method. But it doesn't actually give that much benefit. So it's sort of, I don't know how to think about this exactly, but the two, because it's such a large dimensional space, the tree structure doesn't really impose too much extra sort of extraneous structure on this, you know, but it has the effect of bringing words with, the important thing is that it has this effect of bringing words with similar contexts together. Yeah.
What is this V and H that I didn't get in the formula?
V and H. This one here. No. Okay. So the V is the V is a row of this matrix here that specifies the weights from a particular input to the, so, the VK is the row of this matrix, but in fact that actually just becomes H, because this, one input is 1 and everything else is 0, that vector just gets copied into H. So that's why this appears as H. And then this thing here is these hidden to output weights. Good, very good question.
Output weights. Didn't you say that the second part was thrown away?
After the training. After the training, we just keep the input to hidden weights. I guess. Just one last thing about this tree. So I guess the other way to look at it is to say, well, it may be that there are two similar words that are very far apart in the tree. You know, we were talking about elegant and refined or whatever, you know, if those two words are really quite similar, they may be far apart in the tree, but the tree, even though they're far apart in the tree, the tree may be sort of embedded into the space in a way that those two words do end up quite close to each other, even though they're far apart in the tree. Because if the chops are made in the right places, you can still have things that are close in the space but not close in the tree. I think that's really the reason why this actually still works. Okay, so that's hierarchical softmax. Now, the other method for dealing with this complexity is called negative sampling. In a way, this is actually simpler, I guess, but not as, it doesn't have the sort of same theoretical properties as the hierarchical softmax. So the idea behind negative sampling is the following. It simply says, okay, well, I've got the word that really does exist, that's word J. I don't have time I don't have the resources to compute all the 60,000 other words. So what I'm going to do is I'm just going to randomly pick 10 other words and negatively train them, right? So normally you would positively train the word that really occurs and negatively train all of the others, depending on their outputs. So, but with negative sampling, it's saying, well, I'm just going to pick a random subset. I'm just going to pick very few vectors, very few words randomly, and negatively train them. Yeah. So this is just saying that right, so I pick some subset called W neg of words, and I just, you know, I try to maximize the log of the log of, you know, I take the sigmoid of the output of the correct word, and I take the sigmoid of the output and treat that as a probability. So I try to maximize the probability of the correct word and minimize the probability of some subset of other words, right? So this is, it's related to something called noise contrastive estimation, which we'll talk about much later in the course after the break in terms of image processing. But the thing about this is, it's a fairly simple algorithm. It's not guaranteed to produce a well-defined probability distribution. We don't know whether this is actually related to a legitimate probability distribution or not. So with you know, with hierarchical softmax, we knew it was a probability distribution. Here, it really isn't. So this doesn't really have a solid theoretical basis the way the other models do. But in practice, when you do it this way, it tends to produce pretty good word embeddings. Yeah. Okay. Any questions about this? Would you like me to turn the air conditioning on, by the way? Or I don't know if it's going to heat or not. No, just stay as it is. Okay. It's good to keep us awake anyway. Okay, so just some details of this. So these are things, again, that people just empirically tried a few things and tried to figure out what works best. So for negative sampling, if it's a small data set, normally you pick between 5 or 20 negative samples. If it's a large data set, interestingly, you can often get away with a smaller choice of negative samples. Now, then there's this question about the distribution from which the negative samples are drawn. So I've got this list of 60,000 words, but some of them occur more frequently than others. So should I just choose, if I'm choosing my negative samples, should I choose all 60,000 words with equal frequency? Should I choose each word with the frequency that it actually occurs in the corpus? And these guys mucked around and they tried a few different things. And in the end, this is what they decided. They said, okay, I'm not going to use the absolute frequency. I'm going to use the 1 gram, the unigram distribution based on the previous word. So remember when we talked about Hamlet and you know what the previous word is, so what's the distribution of the next word? They use that distribution, so it's based on the previous word. And then they try, okay, I could just try a uniform distribution for everything. I could try the actual frequency. I could try the square root of the, I could try something between the actual frequency and uniform. So I could try the square root of the frequency. But in the end, what they decided works best is not actually the square root, but the frequency to the power of 3/4. So there's no theoretical basis for this. It's just something they tried that worked okay. So it's halfway between the square root and the actual frequency. I know, this starts to look a bit more like a cooking show than an actual theory lecture. And then the other thing they did is subsampling of frequent words. So some words that occur very frequently, you don't want those words. So this is when this is not the negative sampling, but actually the positive sampling, the words that really do occur. The fact that some words occur more frequently than others can actually just skew the results to some extent. So they say, okay, well, things that occur very frequently, I want to dampen down. So if one word occurs more than another, I still want this word to occur more than that word, but not by quite as much. So in this case, they do actually take the square root of the frequency. And so the way they implement it is I think this is why it's called the skipgram model, is that they throw away some words and they throw away each word with that probability. So if they're throwing it away with that probability, that means they're keeping it with this probability here, which is some proportional to the, inversely proportional to the square root of the frequency. So again, it's just, they tried a bunch of things and somehow, for some reason, this worked. Okay. Now, so that's actually that's the description of the model. Now, what can you do with it? Well, first of all, there are some things we can do, or how would you know? Let's first of all think, well, ultimately what we want to do is use this for machine translation and that sort of thing. But then you can ask yourself, well, how do you know? I said that some people claimed that glove gives better vectors than word2vec. Well, how would you even measure that? How would you measure the quality of word embeddings? If I tell you that one set of embeddings are better than another, how could you measure that? Well, one way of doing it, there's a couple of little sort of tests that we can do to see whether we think these word embeddings are good. Now, one of them is called the sentence completion task. This is something you may see on standardized tests like the Scholastic Aptitude Test, the SAT. You're given a sentence and you're given 4 or 5 words and you have to say which word fits best into that sentence. So, seeing the pictures of our old home made me feel blank and nostalgic. Once you've trained your model, you could take that sentence, you could use those words as the context. And remember, the context gives you a vector, right? So you've got the context. Each of these words is a vector. You can feed in those words, and then you can compute the linear function, which gives you a probability, and the one that tells you the highest probability, that's the one you choose, right? So you can get your model to take the SAT for you. Maybe it'll be admitted into Harvard or something if it's really good. So if you look at it, it tends to do a pretty reasonable job. I mean, wistful, nostalgic, and is a word that's likely to occur in the context of wistful, for example, or home. Sometimes, to answer these questions, you need some sort of logical reasoning, and there's a long history. Some people have criticized these tests by saying that they're culturally biased. So if you look at this question, because the House had the votes to override a presidential veto, the president had no choice but to. What do you think the correct answer is? Anyone want to guess? Sorry? Compromise is correct. But in order to answer this question, you probably need to have some knowledge of the American political system. You know, the president, legislation has to pass the House and the Senate and then be signed by the president. And if the president vetoes it, then it's very complicated when I start to think about it, right? It originally only has to be passed with a simple majority, but then if the president refuses to sign the bill, it goes back to the House, and then if a 2/3 majority vote, then the bill will be passed. So that's called overriding the veto. So people have criticized these tests that they kind of give an unfair advantage to Americans because, if someone from another country tried to answer this question, they wouldn't have it'd be harder for them to answer it. And some of them are considered to be racially biased and so on as well. But anyway, that's an aside. But your model might have difficulty with this too, because if we're just looking at word association, all of those words might occur within that context. So, this sort of shows that sometimes you need a bit more than word association in order to answer these questions. Now, we can also look at regularities. So this has become a very sort of famous example. If you look at I didn't draw a picture of this, but if you look at the vector, remember this is not an affine space, this has a origin, so I can take the vector for king and the vector for woman and subtract. If you look at the vectors for king, queen, man and woman, they actually form a kind of parallelogram, so if I take the king plus woman and subtract off man, I get something actually very close to the vector for queen. In fact, queen is the closest vector to that vector. And this gives us, well, first of all, this gets back to what I was saying at the very beginning. This is something that goes beyond synonyms and antonyms. Often these words are similar in some respects and different in others, and this actually perhaps can separate that out, and ferret out these relationships. So this is another task. This is another thing that appears on these standardized tests is word analogies. So you say evening is to morning as dinner is to what, or bow. Let's look at the second one. Bow is to arrow as what is to bullet. Well, you use a bow to shoot an arrow, so you use a gun to shoot a bullet, right? So the answer is gun. Now, if we look at the way you can use your word vectors to do this is, if you're given a question, A is to B, as C is to what, you can take the vectors for A, B, and C. Right. So the important thing here is it's the angle. you've got the vector for A, B, and C. You get the vectors for A, B, and C, and you calculate vector for C plus the vector for B minus the vector for A. That gives you a vector. And then you've got the candidate word, and what you calculate is actually the angle between the two vectors. So I don't... oh, sorry, what am I looking at here? No, sorry, it's not the... oh, that's funny, okay. No, here it is the dot product. No, sorry, it's not the angle, it is the dot product. Yeah, so this is, because we're word2vec, this is just a probability. This is, if we write it this way, you can see that it's the component of that vector in the direction of this vector. But actually, this denominator doesn't make a difference here because we're only maxing over x. Okay, but so the other point I wanted to make here is that V and C can be swapped here and you get the same answer. So if you look at this top question, I find it a little bit more natural to ask it this way: evening is to dinner as morning is to what? Evening is to dinner as morning is to, well, in the evening you eat dinner, in the morning you eat breakfast, right? But in terms of the vectors, those two questions, it answers those two questions in exactly the same way. If I swap these two, it doesn't make any difference, okay? Any questions about that? Okay, now, and you can draw some nice, interesting pictures with this. So these are some examples where people, again, there's underlying this is a 200-dimensional vector space, but then people have used PCA to extract out the two most significant dimensions. And you can look at examples where you have a country and then you have the capital of that country. And you can see that the vector connecting the country to the capital is sort of preserved, more or less, approximately. Yeah. And then here are some other examples. So capital city, currency of a country, what the money is called, what state a city is in, brother, sister, so king, queen, you can have brother, sister, grandson, granddaughter, and so on. So there's quite a variety here of different relationships. Excuse me, singular and plural, superlatives, and so on. And you can, all of these are preserved to some extent by these word models. There's something, if someone's, if there's anyone Russian in the audience, you might notice something slightly unusual about this. Can anyone see? It's made a slight mistake somewhere. Look at the fourth row from the bottom. It thinks that the president of Russia is a single person whose name is Medvedev Putin, right? Because Medvedev and Putin are so closely associated that it thinks they're the same person. But it can be forgiven for that, I think. Okay, so these are sort of direct ways to test the word embeddings. I won't go into details about this, but this is just something I came across. Someone made a slight variation to this where they tried to combine this with ImageNet. So before, when we talked about ImageNet with those images with in 1,000 different categories. So in this work, these guys were trying to develop these word vectors, but they wanted to do it in such a way that objects that look similar would be close together. So they looked at all those categories in ImageNet And the way they, so let's say there's 1,000 categories in ImageNet, there's 1,000 words there, and for each word you have a bunch of images, and they try to calculate the visual distance between those two objects. But they've got the trained ImageNet that with the CNN, and they pick a deep layer in the neural network, and they look at the activations in that. Let's say they want to figure out the distance between bird and fish. So they look at all the images of birds and all the images of fish, and they calculate the correlation between those hidden node activations for bird and fish, and calculate the angle between them. And then, so they try to make it so that the vectors for bird and fish match that angle, right? So they have a training that does the word to vec as usual, but has this extra term in the cost function. So I mean, this is just sort of like a little bit of fun someone did. It's not really that important, but it's interestingly, it illustrates the idea of combining linguistic and visual information, or trying to impose some additional constraints on the word vectors. But it does produce some slightly unusual results. So clock and pizza end up being quite close together, because a clock and a pizza are both, round with different segments. So, it's questionable whether these things are actually, it makes the network a bit sort of synesthetic, or whatever the word is. Okay, so finally, I just want to talk a little bit about how you can put this together to make serious language processing systems. So this is where we combine, so this is where we take the models that we were talking about last week, and we combine them with these word vectors to build systems. Okay, so the first thing we can look at is translating from one language to another. Let's suppose we want to translate from English into French. There's a very good database, because the Canadian Parliament, everything in the Canadian Parliament, everything that's said in the Canadian Parliament is translated either from English into French or the other way, and people check the translations and make sure that they're very accurate. So here you have an English sentence: economic growth has slowed down in recent years. And the corresponding French: la croissance économique s'est ralentie ces dernières années. Now, of course, English and French are fairly closely related languages, admittedly, right? And the word order is pretty close in the two languages. Sometimes we see the noun and the adjective swapped or something, but it's, relatively speaking, it's fairly close. So the first way you might think to do this is as follows. So we've got our word embeddings. So we've got this sentence, the input sentence. For each word, we have our word embedding that we've trained with GloVe or word2vec. So we look that up effectively in our table and put in that word embedding, and then we feed that into a recurrent neural network. So this could be a simple recurrent network, or it could be a long short-term memory. But whatever it is, we have hidden units, and we feed in the next word, and it gives us a new hidden unit. And we feed all the words in one by one. Right, so this is the simplest model, and then we'll look at a couple of later enhancements. So here we feed the words in one by one. We have the hidden unit, and then in the end we have the last hidden unit is, in this model, the last hidden unit is meant to contain to encode the entire sentence in some sense. And then we take that hidden unit and we do the process in reverse. So we have another LSTM at the top with hidden units, with the hidden unit activations, and we so from this hidden unit we generate the first word in the sentence, and then we feed in this model we feed in the previous value of the hidden unit, we feed in this the values here, and we also feed in the previous word, and combining all this together we generate the next word, and so on. So you sort of, it's like a thing where you roll up a carpet in one language and then you sort of unroll it in another language. Now, this gives reasonable results for short sentences, but there's a bit of a problem here that you're hoping to capture the entire sentence in that one hidden unit. Now, it depends on, for translation, this is sort of stretching things a little bit. This is actually good for some other tasks. So, like sentiment analysis. Now, so this is actually, this bottom part is actually kind of what you'll be doing for the second assignment, which is going to be released later this week. You'll be looking at sentiment analysis of movie reviews. So you'll be inputting a movie review using some pre-computed vectors. So we'll give you some pre-computed vectors that have been computed using GLOVE, and you'll be processing the movie review, and then at the end you have to say whether it's a positive review or a negative review. So for this kind of task, this model is quite reasonable, because it's reasonable to expect that all the information will be contained in this last unit. If you're just trying to sum up the entire sentence and say whether it's positive or negative, you can reasonably expect all the information to be here. But if you're doing machine translation, it's a bit ambitious to think that all of this will be encoded just in here. Okay, so what can we do alternatively? Well, we can have what's called an attention mechanism. Okay, there's one more thing here, is about forward and backward. So the other thing is that sometimes you need information from later on to make sense of a word that happened before. Normally, obviously, it's more common that you need information from a previous word to understand a later word, but sometimes it can happen that a word that happens one or two later tells you the meaning of the previous word, right? So, in order to capture that backward information, sometimes they have hidden units going in the other direction. So they have one LSTM which is processing the words in a forward direction, and they have another LSTM independently processing in the reverse direction. So it's looking at the words from the last word back to the first word, right? So that's one enhancement they have. So they have these two hidden unit activations, and then the other enhancement is what's called an attention mechanism. So the way this works is I process the whole sentence, and I have hidden unit activations at each step of the way. And yeah, I have two sets of hidden units activations. One is the forward processing, and then one is the backward processing. And then instead of when I'm translating up here, instead of taking just the right-hand side hidden units, I'm actually taking a weighted sum of all the hidden units. And then that weighted sum is feeding into my hidden unit activation to help me determine the next word. And the weights in this weighted sum are also chosen by backpropagation. So this sounds a bit, strange at first, but it actually improves the performance massively. And the way to think about it is as follows. So, as I mentioned, in English and French, the word order doesn't usually change too much, but in some languages, the word order changes a lot. In Latin or Japanese, the verb goes to the end usually. German, the word order in German can be a bit different as well. So, the main thing this attention mechanism does is it tends to focus attention on the part of the sentence that you're currently translating. So if we think about this as not English and French but something else, it could be that the first few words here are actually translating something later on in the sentence. So what will happen is that somehow the attention mechanism will initially focus on that part of the sentence that gets translated first, and then it'll somehow learn to reduce the weighting of that part of the sentence because it's already been translated. So it sort of kind of identifies which parts of the sentence have already been translated, and among those that remain, which is logically the bit that should be translated next. Yeah. So this is the attention mechanism. And so finally, putting all of this together, we get something really on a serious industrial scale, which is the Google neural machine translation. So I can't go obviously through all the details, but I'll just point out the salient features. So what happens here is, so the bottom bit here is what I described here. So you have two sets of long-short LSTMs. One is processing the sentence forward, the other is processing it backwards. And then you have what are called stacked LSTMs. So you have another layer of LSTMs here and another layer of LSTMs here, and each layer of LSTMs is feeding into is treated as the input to the next layer, and these are residual connections. So all of these ideas that we discussed before are kind of coming together here. We talked about residual connections in image processing. This is exactly the same idea, but it's being used for language instead. And there's 8 layers here, and then we get this. So again, the residual connection, and then, so that happens in the source language, and then the same process happens in the target language. Again, there's another 8 layers of stacked LSTMs, and there's an attention mechanism that weights them. Now, so what's the purpose of this? Well, why do we have these stacked why do we have these residual networks? Well, it's the same idea as for the image processing. What happens in effect, because of these skip connections, there's a skip connection here, 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 here. There's only one layer in between here, not 2 layers. And so when the differentials are back propagated, the differentials can go all the way back through the network directly to here. The same differentials, the differentials from the output layer are copied unchanged back to all of the layers, and then the differentials from the last layer is copied back, and so on. So what actually happens is that the lowest layer attempts to do the entire job, and then the next layer just tries to correct the mistakes that were made by the previous layer. That's basically the way it works. So each layer either tries to correct the mistakes of the previous layer or tries to fill in additional details that was beyond the capability of the previous layer. And some aspects of this were done for the sake of parallelization. So if you'll notice at the bottom layer here, they have forward connections and backward connections, but at every other layer, they only have forward connections. So that's for two reasons. So first of all, as I said, in language, the majority of information happens forward in time. But they also partly did this for computational efficiency. They realized that somehow they could parallelize a lot of, because this top part is feed forward, they could parallelize a lot of the training in this part of the network. If they had backward connections at each layer, it would slow the process down and make it harder to parallelize it. Yeah, so some of the design decisions were made for that reason. Okay, any questions about this? Yes?
Translation, a couple slides back.
Yeah.
Does that assume a one-to-one? Like, how do you know how many words should be in the translated sentence?
It doesn't have to. Oh, okay. The question was, how does it assume how many words should be in the sentence? It doesn't. The number of words doesn't have to match up. I think it just there's some marker. Oh, okay. That's a very good question. So how does it know when to stop? Effectively, I think the answer is that there's a special, like a full stop, like an end of sentence is treated as, or end of translation is treated as a sort of word, as a symbol, and then when it gets to that, then when it predicts that the next symbol is the end of, the stop signal, then it stops. Yeah.
So it doesn't assume a one-to-one translation. Because some words like beautiful girl.
Right. Yeah. Petit déjeuner is breakfast or whatever. Yeah.
Because up there it has the same number of nodes. Is it a variable number?
It's a variable. The number of nodes. Okay. So I think. Okay, that's a very good question. So I think what happens is this: that for the decoder, probably also for the encoder, you see this symbol here. Okay. It's a bit hard to see. Let me see if I can zoom into this. You see there's this symbol here that's dot close bracket. I think that dot close bracket is a special kind of pseudo word that means it's the end of the sentence or the end of the utterance. So when you're training, you input that. You treat it the same as another word, basically. And then when you're decoding, it's the same thing. And so when the model predicts the end of utterance, that's when it stops. Yeah. That's a very good question. Yeah. So it tries to, so it could, definitely there can be a different number of words in the output compared to the input, but the attention mechanism tries to make sure that every part of the input does get translated somehow. Okay, that's funny. What direction are you? Okay, then this, well, this is just another example of, this is from, I think, Fei-Fei Li's group at Stanford. This is another example of combining images with language. So in this case, the task is that you're given an image and you have to come up with a caption for that image to describe what's happening in that image. And so you process the image with a convolutional network. So this is what we were discussing like last week or the week before. And then the convolutional, you have some convolutional layers, and then, sometimes you have fully connected layers, but maybe you want to preserve some spatial relationship here. And then again, you have so these weights here from this deep layer of this image processing network play the role that was previously played by the input sentence, right? So that gets here, and then you can have an attention mechanism. You could have vectors that represent, say, these different portions of the image, and then you can have an attention mechanism that weights these different parts of the image, and then this part is, the same architecture as before. You generate a sentence, and the attention mechanism allows you to just possibly describe multiple parts of the image. So the caption here is a man is jumping into a lake. Yeah, so you have to find the man and then find the lake. So it's it's quite impressive that they can do this. I mean, the accuracy isn't fantastic, but the fact that they can do this at all is really quite impressive. Okay. There's only yes.
Quick question on that one.
Yeah.
Does that rely on being pass an image, not just holding it as a whole?
Yes, it does. So we've got a bit of time left. This is not really. Well, does anyone have any final questions about this language stuff? Yeah. So what I thought I would do, I'm glad you asked that question. What I thought I'd do, I'd just maybe take another 10 minutes or so to explain actually a system which does exactly that, which segments parts of the image. This is not I won't do it in detail. It's not it's not sort of examinable, but just to give you a bit of a flavor of it, because this is something that's quite impressive. So I don't know if you've seen this system, but it's called the YOLO 9000. Let me see if I can find a video of this for people who haven't seen it. I don't like the music, but you like it? Okay. We can have it at low volume if you like.
I wish she'd get a seat, but she only cares when she's got the time. And I fret so much about her love bed. I wish she'd let me be, but her destiny's got us intertwined.
So there's a few videos of this, but this one is good because it shows quite a variety of different objects. So you see here, it's picking out a person and two dogs. And then here we got a truck and a car and some people. And then, people waiting for a train, okay. So, it thinks that's a chair. Actually, that's not. It does look a bit like a chair, actually, but yeah, it's not really. Okay, so it's not perfect.
I wish she'd get a seat, but she only cares when she's got the time. And
Okay, yeah, motorbike. It's pretty good. It occasionally makes a mistake, but when you think that objects are sometimes occluded, horse. I mean, a horse and a, yeah, I suppose that is a small horse, isn't it? Oh, it thinks that's a dog. If you look closely, you can see it's impressive that it picked up the backpack. But yeah, it thinks that's a dog. Where's maybe? So you could see the variety of this, right?
What is she thinking?
Dining table, bowls. All right. So again, like I can't say all the details, but I just want to say a little bit about this, and I'm just using these slides from the authors. So roughly speaking, how does this work? Well, it takes the input image, it splits it into grids, it looks for bounding boxes, so it has to try to, it's not just, this is different from ImageNet. So it is trained using ImageNet. It's trained on objects that occur in ImageNet, but the task is quite different because it's not just taking the whole image and saying, oh yeah, that's an image of a bird. It's actually trying to find little bounding boxes and identifying objects in those bounding boxes. Now, this was previously done with what's called an RCNN, but yeah, so they got a convolutional network, and then the output is trying to predict the boundaries of the bounding box and the object. Now, in slightly earlier work in this field, the network was actually just trying to output coordinates. You know, the box goes from pixel 54 up to pixel 100 or whatever. Now, one of the enhancements these guys did is, yeah, so again, this is, in a way, this is about engineering more than anything else, but they actually analyzed this huge set of images. So they use the ImageNet images, but there's another database called COCO, which actually is labeled images with multiple objects in them. And so they analyzed all those images and tried to identify a set of sort of generic bounding boxes within images that objects typically occupy. And so their network, instead of giving the absolute coordinates of a bounding box, it selects one of these reference bounding boxes and then just says how much to shift it by. You know, take this generic box, but then, you know, add 5 pixels in this direction and 7 pixels in that other direction. So that actually kind of improves the accuracy quite a bit compared to just trying to predict the coordinates. And this is, the description of their network. As you can see, it's got convolutional and pooling layers and so on. Now, and again, this is interesting because multiple ideas coming together. So they used they use a hierarchical description of different objects. Yeah, so you might, a dog and a wolf or a dog and a fox look quite similar, or there's often objects where you're not really sure like what level of detail to classify them according to. So they actually use this kind of hierarchy of objects that they derive from WordNet. So, things are classified as an animal or an artifact or a natural object. And then within animals, you have cat, dog, and fish. And within dog, you have different types of dog. And this is more or less a tree, but occasionally things do loop and come back into, I don't know if there's an example here, but it can happen that, there's some objects here that there's that there's alternate paths to the same object. It doesn't happen very much, but it is possible. And this is actually kind of beneficial as well, because here it's hard to read this, but it's classified both of these as dogs, but this one is classified as a German Shepherd, and that one is a Siberian Husky. So it's sort of, if it makes a mistake, it's not a total mistake. Often it classifies it as a nearby object, or gives you some information about the identity of the object. And in some of those videos, it actually, you see a person being classified as first as an organism, and then as a person, and then perhaps as a merchant or a businessman or something like that. So it's, comes down to different levels of detail depending on how confident it is. Yeah, athlete, contestant, okay. So how did we, you were asking about, yeah, so I think that, I don't know all the details about this captioning, but it probably uses some system a bit like this, but maybe not quite as, probably wasn't quite as advanced as this, yeah. And they've also applied this to video somehow. They analyze a video and they come up with a caption saying that a woman is boiling a fish or something like that. Good. Okay. Thank you for your attention, and we'll all go home a little bit early.